Okay, hi class. Welcome to the 1 p.m. class today. So today we'll be going through the second part of units of measurements. So if you have whatever your teacher have done so far, most probably will have done the prefixes, base units, derived units, um, and then to a certain extent, some schools might have already done your vernier calipers and your micrometers. Some might even have finished pendulum. If you have not finished pendulum, don't worry. Today I'll go through some basic concepts of it before we go and look at the questions. All right. So let's look at the question itself. Okay. The first one, which instruments are most suitable for accurate measurement of the thickness of a coin and the internal diameter of a test tube? Okay. So the key thing, internal diameter of a test tube is a round object, cylindrical object. It has to be under vernier calipers. So you'll be likely option B or D now. Thickness of a coin. So a coin is not a very thick object. And we all have coins. So it's actually pretty thin. So for things that are small, we always use the micrometer. And therefore that will give us option B. Okay, next. Now this, if you look at the readings, 120 mm, 5 mm, 3.2 mm, these are all about the accuracy that of vernier calipers, micrometers, and your ruler. So let's look at vernier caliper first. So vernier calipers will be up to 2 decimal place of a cm. So for example, 2.32 cm. If it's 2 cm, just at 2 cm, you'll have to write it as 2.00 cm. Okay, micrometer will be 2 decimal place of a mm. So for example, 1.22 mm. Again, if it's exactly 2.00 mm. So if you look at this 120 mm, most probably it's going to be a meter ruler. Next, your 5.0 mm, if I convert it to cm, it will be 0.50. So this will give me my vernier calipers. All right, likewise, 3.2 should be a similar manner. So will be option 1 and 2 only. Okay. Okay, let's look at the next question. Similar to the previous question. So vernier calipers and micrometer screw gauge. So when you see this type of questions, before you actually look at the options, you should write down somewhere near, below, or above the vernier calipers and micrometer screw gauge what you remember about the accuracy. So vernier calipers, 2 decimal place of a cm. This is an example. 2 decimal place of a mm. So look at A and B. 5.2 cm, 1.3 cm. This one will be vernier caliper. This one likely is not. So A is out. B, both are 1 decimal place of a cm. So definitely cannot be micrometer or vernier caliper. So B is out. Okay. C possible. But this is a tricky one. So let's KIV first. Let's look at D. 5.22 cm definitely is a vernier caliper. 1 cm, neither vernier caliper nor micrometer. So D is out. So see what I've done here is I eliminate, then left with the logical choice. I choose that for my answer. All right, sometimes in MCQ, you cannot really know the answers straight away, especially hard MCQ questions, whereby the options are sometimes very similar. You really need to think about it. Then you might have to go and look at doing this method, elimination. So let's go back to 1.33 cm. So if you look at 1.33 cm, if I change it to mm, I times 10. which is 2 decimal place, which is fits the micrometer screwage. Therefore, answer is C. Let's look at the next one. Okay, so for those who have not learned pendulum yet, I'll use this question to go through some of the key concepts you need to know. So first of all, what is the oscillation? So let's look at P as my starting point. To Q, to R, go back to Q, go back to P. That itself is one complete oscillation. So you know what is, sorry. You know one complete oscillation. Next, the time taken for what I've just described, go from P to Q to R, then back to P, that is one period. Okay, and it's very often in this chapter and maybe waves, you will see this represented by the alphabet capital T. Period. Next is frequency. Frequency is in 1 second, how many complete oscillations are there, or how many complete waves are produced. So frequency F. And the relationship between frequency and period is given by this formula. Frequency equals to 1 divided by period. So keep this in mind. Later we might have questions that involve this formula. All right, so these are the 4 key things you need to know. The next is what will affect a period. Right? What will affect a period is always dependent on 2 things, and 2 things only. G, your gravitational field strength, yeah, inversely proportional. Your G increase, your T will decrease. And this time taken will be shorter. All right. The other one will be your length. We're talking about length of the pendulum. Length, capital L or small l, depending on the question. Your L increase, your period will increase. All other factors does not change. One will be your angular amplitude, angular displacement, how far you pull and the angle they make. That does not affect the size of the bob. The bob is the ball. We don't call it a ball, we call it a bob of the pendulum. Bigger mass or smaller mass, as long as the length does not change, the period will not change. All right, so let's look at this question. If the period is 2 seconds, so that means from P to Q to R, back to P is 2 seconds. What is the time taken? It moves from Q to R. So you look at the arrows that I've drawn, there's 4 quarters. So you take the period 2, divide by 4, you get half, which is 0.5. Therefore, it's option A. Next, what is the period? X. It takes time to swing from X to Y and back 20 times. So you see, 20 times. So your period, you cannot straight away take 9.4 because 9.4 is for 20 times. So you need to take 9.4 divided by 20. And you should get 0.47 seconds. Option A. The time taken for pendulum to swing from A to B is 0.2. So now a bit you play around with it. So A to B is half an oscillation. So A to B 0.2, B to A will also be 0.2. And this question is asking for one complete oscillation. So with 0.2 plus 0.2 or 0.2 times 2, you get 0.4 seconds. Option D. Okay. There's another form of oscillation that is similar but not so common, but it's a bit trickier. So let's use this as an example. So imagine there's a point Z here. So one complete oscillation will be from X to Y to X, X to Z, go back to X. Okay, you see, 4 quarters. So it's one complete oscillation. So from X to Y is 1.5 seconds. That means it's 1 quarter of the oscillation. So I take 1.5 times 4, or could be 1.5 plus 1.5 plus 1.5 plus 1.5. You will get 6. Therefore, answer is option D. Yeah, it takes 13.8 seconds for pendulum to swing from X to Y and back again 20 times. So this will be similar to just on that question. We've got to take 13.8 total time taken divided by 20. So period or T will be 13.8 divided by 20. And you should get 0.69 seconds. So the question is, why do we take it always 10 times or 20 times? Because if you just do one complete oscillation, sometimes due to human reaction time, your responses might not be so fast. So the time taken for the complete oscillation might not be accurate. So to reduce this type of error, which we know as random errors, usually we'll take 20 times, 10 times. Then we take the average. All right, then repeat. Then I take, so I got 2 average, right? Add up, I find the average of that. This process will help to reduce random errors. Okay, there's 2 types of errors. One is random, one is systematic. Systematic errors means there's issue with the machine you're using, the device you are using, and you know what is the error. You always know what is the error. Random error is a bit, error is not so known and predictable. Okay, so this back to this question. So for question 8, the answer is B, 0.69 seconds. So let's go on to the next question. Okay, the swings of a pendulum of fixed length. So fixed length here means the length of the pendulum does not change. Are 10 degrees wide, and each complete swing takes 1 second. If the swing is reduced to, 10 degrees wide, if the width of the swing is reduced to 5 degrees, each swing will take. So if I draw it out, it looks like this. So the first one will be this. This is 10 degrees. Second one, 5 degrees. So the length won't change. Only this angle change. So if you remember what I said earlier, the angular displacement does not affect the period. So if the length don't change, and the original period was 1 second, with the new angular displacement, the period will again be 1 second. Option C. Okay, let's look at the next question. Number 10. Weights attached to 2 suspended strings are given small displacement and allowed to swing freely. Basically, you take out, let go, and then just go. Their periods of oscillation will be equal if they have the same length. Because length is on the same planet, so length will only be the only deciding factor for your period. So therefore, length of the string will affect the period. So if you have the same length, then you have the same period. So option A. Let's look at the next question. What is meant by the period of a simple pendulum? This basically is asking you for the definition of period. Also, time